Good afternoon, everyone. My name is Vijay Kumar. I work for ATM Systems Private Limited from Bangalore, India. So my topic is cloud-based workflow for AVC film grain synthesis. I am the co-author, and my colleagues, Mr. Kaustubh and Mukund, are also the co-authors of this paper, and I am presenting on behalf of them. Following is a brief outline of this presentation. We'll have a quick introduction to film grain technology, followed by the cloud workflow and some of the key components of the workflow. We'll touch base on some of the grain estimation process which we have explored, and we'll conclude with some results and observations. So some of the keywords used in these presentations, I just wanted to highlight so that it's familiar for the audience. The film grain SCI message, FGC SCI stands for Film Grain Characteristics SCI message, part of the MPEG standards. FGS stands for Film Grain Synthesis Process, and FGS Rewriter stands for the bitstream editing utility, which can be used to insert or alter SCI messages. The other terminologies have been very common, and we have been discussing from the morning, multiple codecs. WSM stands for WASM technology, WebAssembly, and JS stands for JavaScript. So film grain technology has been part of multiple coding standards. As a part of AV1 standard, it is a mandatory process. The process is standardized, and the synthesis is defined in the specifications. It supports autoregressive model, whereas in the MPEG standards, the process is not standardized, and it is optional. It is part of the SCI message, and it has provision for two models, frequency filtering model and autoregressive model. The classical use case for film grain synthesis has been in the handling of input with camera noise, where the noise is denoised and the removed noise is modeled as film grain parameters and signaled as metadata in the bitstream. On the decode side, the parameters are used to resynthesize the noise and apply to the video to recreate the original look of the video. The application which we are going to discuss in this presentation in more detail is how film grain technology can be used to masking video coding artifacts. The idea here is that the original content doesn't have any noise, but we can artificially add comfort noise or subtle noise which can help in masking the artifacts and also increase the sharpness of the video depending on the content. Following is the high-level workflow diagram. It is basically designed on a classical server-client model. All the client-side applications are used for continuous monitoring and quality control purposes. The workflow is targeted for contents without film grain, and which is already pre-encoded and stored in the cloud. So the low bitrate representation of these contents can have a lot of artifacts, and these are considered for film grain insertion. During the process, there is no re-encoding or transcoding done, and only the necessary parameters are inserted without affecting the coded layers. So the components which are key in the workflow, which are run on the server side, can be an SDK or a container, which can be used as it is, or it can be customized based on different use cases. It has mainly 4 components: application controller, which takes care of interface of the data between the different components; the film grain estimator, which is the model responsible for estimating the suitable noise for different content; the SCI inserter, which will take care of inserting the right SCI messages into the content; and the publisher as a dash segments. So some of the key tools which are being developed as a part of this workflow are also made available on GitHub for public use. The film grain synthesis module, the film grain SCI rewriter module, and an AVC decoder, which exports, after parsing the SCI messages from the bitstream, it exports the SCI messages outside. So these components are available on GitHub. We have also developed a demo player using these components and hosted on AWS Cloud. Please do check out these links. So we'll have a little bit of detailed discussion of some of the key tools inside the pipeline. So the rewriter is a low complexity utility supporting 2 modes of operation. It has a mode of operation to edit existing SCI messages if you want to change the strength of the film grain noise or the cutoff frequencies. It can be edited appropriately. Or if there is no SCI present in the bitstream, it can insert a new SCI message. Currently, the open source software available on GitHub is supporting AVC syntax and AVC bitstream editing. It can be extended to VVC and HEVC as well going forward. The film grain synthesis library is the core component responsible for synthesizing the noise on the decode side. So the library is compliant to SMPTE RDY specifications, and it supports frequency filtering model. The library is optimized for both Intel and ARM processors, ARM architectures, AVX2 and Neon SIMD. The interface is simple and synchronous and has the ability to configure FGC SA parameters at every frame level. It also supports multi-threading up to 8 cores with support for in-frame parallelism, which not only helps in improving the performance, but also reduces the latency of the processing. The table here captures the performance of film grain synthesis library on a single core general laptops and mobile devices. So the processing time is in the order of 1 to 2 milliseconds for a 1080p resolution, which is indicating that it is super real time. So any decode pipeline can accommodate this process as a post-processing component without having any major processing overhead. The film grain video player designed for browsers is also a mini server client model. So it is developed based on WSM technology. On the cloud, the WSM compiled library, the application, and all the files are hosted, and these files get loaded onto the browser during runtime. The unique advantage with WSM is that the single library can help in, can operate on multiple target devices. Like same library can get compiled on Intel or ARM, depending on the target architecture, and the assembly level language is converted runtime. The browser player is validated on all standard OS, Windows, Linux, Android, and Mac OS, and also is validated on all the popular browsers like Edge, Chrome, Safari, and Mozilla Firefox. So coming to the grain estimation process, this is something which has a lot of scope for research and experimentation. There could be multiple methods and multiple approaches which can be considered. The overall objective, what we have identified is that this module should take care of, first of all, qualifying whether a particular content or a scene can benefit from film grain SCI insertion. It might so happen that the extent of blockiness or the artifacts are too high, and film grain may not be able to benefit a whole lot, or it might have very less artifacts due to high bitrate encoding, where any noise insertion only will decrease the quality instead of improving it. So we need to identify whether the current set or current scene is eligible for film grain SCI insertion, and then once it is qualified, then one of the approaches which we are currently pursuing and under research is to identify whether the content has low spatially low variance areas, which are which our human eye is very sensitive to. So any blockiness or any artifacts in these areas are easily noticeable. So first is to see if we can mask these artifacts with suitable noise. So once we identify and demark these regions, then we need to look at the intensity intervals or the pixel values inside those regions and come up with the corresponding strength of noise and the grain parameters which can be used for SCI insertion. So based on our initial experiments and some of the tests, so following are the results. So when we looked at objective assessment, right, we were looking at different matrices. In this scenario, there is no access for the reference, meaning there is no input video available for us to compare the score. So that's why we ended up using the BRISC metric, which is the blind referenceless image spatial quality evaluator, conceptualized and developed by University of Texas, Austin. So this is a non-reference metric to evaluate image quality in spatial domain. We have also extended this to work on videos as a group of images. The scores ranges between 0 to 100, where a lower score is always indicating a higher quality. So what we did was we took standard 1080p contents which are available online, and then encoded them at bit rates ranging from 3 megabits per second to 6 megabits per second, and then computed the BRISC scores with and without film grain. For each content, the film grain parameters were different, and it was because of the characteristics of the content, the corresponding strength and the cutoff frequencies were different. So looking at the scores, we can easily say that with film grain synthesis, the quality is better. But as you can see, the amount of gain varies based on each content. So it is very content specific. So we also conducted subjective assessment of the results by side-by-side comparisons. And some of the screenshots are shared here, and a few more are available in the paper. So mainly what we have to say, look for is that the background areas which are flat are more susceptible to banding and contouring, and those gets masked very effectively using film grain. And also the text region is not getting distorted a whole lot with film grain synthesis. So these are some of the key things, and also the overall sharpness increases. The screen might not be representative, but I think a close observation would give those results. So overall, as a conclusion, so based on BRISC scores and also the subjective assessment, we feel that film grain synthesis helps in masking artifacts and improving the sharpness of the video. So the entire workflow which is available, components and the full workflow which is available can be used for SCI insertion without any need for any re-encoding or transcoding. Film grain synthesis also can work as an aid or a bitrate saving tool indirectly, right, without having any impact on visual quality. The film grain synthesis process is very lightweight and adaptable across MPEG standards. The implementation is such that it is consistent and bit accurate across multiple devices like TVs, laptops, mobile devices, etc. Thank you.
Thanks, Vijay, for being on time. That's awesome timing. So we have a minute or two for questions. Is there a question here? Ah, we have some questions. There's no mic. I'll give you mine.
Hi. So my question is, have you tried similar modeling on input that does have film grain to remove it and then reinsert it and see how that behaves?
Yeah, so we have a separate workflow for that where the noise is available to us, meaning the input noise is available during the denoising process, and we are trying to estimate how closely can we represent using the film grain parameters. Right, that's a different workflow and a different use case which I have described. So that is also available, but this is something which is not part of that pipeline, right? There is no film grain noise in the original video at all, right? So we are introducing some artificial noise to it, which, with which it can benefit, and some of the contents can look better when watched visually. So that is the use case which we have discussed. So we do have that.
So very quick question. There was a parallel effort to achieve exactly the same RDD5 in case of HEVC, in X265, and in FFmpeg. Have you looked at these and their performance?
Yeah, so we have benchmarked the performance. I think it's more or less better than whatever is available in FFmpeg, the synthesis process in terms of its computational complexity. Right? And so the VTM software also has a similar process adapted, and that was contributed by TM. So it's the same process. Yeah.
Right, another round of applause for Vijay Kumar, please. I think we'll stop.